In this unit 3.2, we will see the thermodynamic and kinetic fundamentals of chromatography. We will define the basic chromatography parameters such as retention time, capacity factor, selectivity factor, and resolution. Then we will explain the theoretical place theory, as well as we will review the main kinetic aspects of chromatography. We will propose some possibilities or mechanisms to improve achromatographic separation. And finally, we will see the quantitative aspects of the chromatography. The last slide, of course, as in Unit 3.1, you will see the bibliography that you can consult. The thermodynamic and kinetic aspects of the chromatographic separation are mainly reflected in the location and shape of the chromatographic peak corresponding to each solute. Thermodynamic aspects govern the equilibrium distribution or partitioning of solutes between the two phases, mobile and stationary phases, and are therefore responsible for such important characteristics as retention and selectivity. Kinetic theory explains in quantitative terms the chromatographic peak shape as well as the effects of different variables on the peak width. The peak location is specified by the retention, which is defined as the delay suffered by the solutes present in a sample on a chromatographic column in relation to an unretained compound, both being subject to identical conditions. According to this, the first parameter to talk about is retention time, which is the time it takes for the maximum of the peak to appear. The basic time, T0, is the time it takes for a non-retained compound to appear. And the corrected retention time of a solute, Tr', is the retention time minus the basic time. Basic time, T0, can be calculated or estimated by multiplying the volume of the column by the flow rate at which the sample is circulating, taking into account the porosity of the column. But generally, basic time is experimentally obtained by passing a non-retained compound. That means not having interactions with the stationary phase chosen. A parameter of major importance to further characterize a solute in a chromatographic system is the so-called capacity factor, K lowercase. It's a parameter that describes the migration speed of solutes in the stationary phase. It's calculated as the relation between the corrected retention time for each solute and the basic time. It's independent of the system geometry. The longer the retention time of a component in the column, the higher the capacity factor. Ideally, it should be between 1 and 5, because if the value is higher than 5, the retention times are too long, thus increasing the analysis time and bandwidth. If, on the other hand, is less than 1, the retention times are too short, hindering the determination of a solute. In planar chromatography, the retention factor is calculated as the quotient between the distance traveled by the solute and the distance traveled by the solvent. Finally, the distribution constant, Kd, measures the distribution of the solute between the mobile phase and the stationary phase, which is the principle on which chromatography is based on. CSP and CMP correspond to the molar concentrations of each solute in the stationary and mobile phases respectively. Ideally, It's constant over a wide concentration range within which linear chromatography is established. For this reason, a quantitative calculation of chromatographically separated solutes can be made, as we will see later on. The selectivity factor, alpha, measures the relative separation of solutes 1 and 2 that are adjacent peaks. Is defined as the quotient of the capacity factors of these two compounds. According to this, it's always greater than 1, which means that compound 2 has longer retention time. This is a dimensionless quantity. However, this parameter doesn't take into account the width of the peaks, which also determines the quality of a separation. This consideration is taken into account by resolution, the next chromatographic parameter we're going to see. Resolution is defined as the quotient of the difference between the retention times of two adjacent peaks, solute 1 and solute 2, and the mean width of the band at the baseline, as shown in the formula. The bandwidth, W, is estimated as 4 sigma, the standard deviation of the peak, as the width of a Gaussian curve is directly related to the variance. Therefore, let us keep in mind that this definition is based on the premise that chromatographic peaks present a Gaussian distribution. We will see that this is not always the case. Resolution is a dimensionless quantity and by definition is always greater than 0. A practically complete separation of the peaks at baseline is considered when resolution is greater or equal to 1.5. If resolution is equal to 1, the peaks touch just as they reach the baseline. And if resolution is less than 1, the compounds come out mixed. As a practical example, we can see here the towers where the different petrol fractions are obtained by following a fractionating distillation scheme. In this case, at each stage of the tower, the liquids of a given boiling point condense and are collected in a vessel. In this way, the different components of petrol are separated. For example, bitumen, lubricating oil, diesel fuel, paraffin, naphtha, gas. In each of them, the equilibrium of the solute occurs between the liquid and gas phases, which is governed by the thermodynamic laws. Lyman C. Craig used this theory for fractionating liquid-liquid extraction. Counter-current distribution is a separation process that is founded on the principles of liquid-liquid extraction, where a chemical compound is distributed or partitioned between two immiscible liquid phases, oil and water for example, according to its relative solubility in the two phases. The Craig counter-current distribution apparatus is shown in the picture. It consists of several connected tubes with upper and lower compartments, filled respectively with two immiscible solvents. The first tube contains sample dissolved in either the upper or lower immiscible liquid phase. The lighter liquid phase, the upper one, is transferred from tube to tube, while the heavier phase settles down on the bottom of the tube. After the lighter phase is transferred from the first tube to the second tube, more solvent is added to the first tube, and the process continues until all the tubes are used. Eventually, The last tubes hold only the lighter phase, and the first tubes hold on the heavier phase. The amount of solute that is equilibrated between the two phases depends on the distribution coefficient of the solutes, Kd, and the relative volumes of the two phases employed. Moving to chromatography, this theory assumes that the column is composed of n layers or segments, which are the theoretical plates, and the equilibrium between the two phases, stationary and mobile phase, takes place at each one. As theoretical plates are generated during the elution of solutes through a chromatographic column, contain a wealth of information about the separation process, mainly peak dispersion. The number of theoretical plates forms the basis of chromatography theory and is a key parameter used in all modes of chromatography for measuring column efficiency. We are going to see how to calculate column efficiency in terms of N. Peaks eluting from a chromatographic column can have a Gaussian distribution. This is to be completely symmetrical. In this case, N is defined in terms of the peak distribution as shown in the upper formula. The width at the baseline for a Gaussian peak is equal to 4 sigma. Joining both expressions, we get the formula in the blue box. It's also possible to calculate N taking into account the width at half peak height, which is 2.35 sigma. And then we get the formula in the yellow box. Why and when we employ one formula or the other? There are occasions when, if the resolution between peaks doesn't occur at baseline, this is for a resolution less than 1.5, we must resort to measuring the width at half-height peak. However, the reality shows that most of the eluted peaks of a column present some asymmetry. One way to estimate the number of theoretical plates with peaks of this type is to draw a horizontal line across the band at a height equal to 1/10 of the maximum height to get the width of the peak at this point. And finally, we get the formula in the green box. The asymmetry, therefore, can be defined as the ratio between the two segments of the chromatogram, BC and AC, defined from the vertical line starting at the peak maximum. This asymmetry can affect the quantification of the peak and its error, because as this value increases, the peak tailing increases. In the example presented in the slide, the influence on the quantification when asymmetry increases from 1 to 1.58 depends on the peak integration criteria selected. If asymmetry is equal to 1, we are dealing with a total symmetrical peak. Therefore, the way the software integrates the peak has not relevance. We can see the recovery area by peak integration is changing from 99.9 to 99.6%, all of them quantitative values. On the contrary, if the asymmetry rises to 1.58, the quantification of the peak can go up to 5% loss. Being the recovery area by peak integration changes from 97.8 to 92.3% in this example. This is not an acceptable loss value for a compound quantification. It's also possible to calculate the efficiency of a column with the equivalence plate height term, H, which is the number of theoretical plates per unit length of the stationary phase. The formula is shown in the blue box. Both N and H can be calculated for each chromatographic peak, but an average value for the column can be estimated. These values shouldn't change much for compounds moderately retained by the stationary phase, but generally increases for highly retained compounds. Now, the lower the height of the theoretical plate, H, the higher the number of them, N, in a column of fixed dimensions, and therefore the higher this column efficiency. Why? Because a greater number of equilibria or fractionations of the compound between the stationary phase and the mobile phase is happening. As a conclusion of this theory, efficiency measures the degree of band broadening that a compound undergoes across the stationary phase. And then, the longer the retention time of a compound, the more it will broaden. As a summary of this theory, the terms selectivity and efficiency are both of high relevance to getting a good separation. This is shown in the example given in the slide. In both cases, the resolution is the same because we have the two adjacent peaks conveniently separated at baseline. However, we are facing two different situations. In the first one, the two peaks are close together, meaning low selectivity, but very narrow peaks, high efficiency. Therefore, the denominator of resolution is small, leading to a convenient resolution value. In the second case, peaks have more differentiated retention times, meaning high selectivity. But peaks are quite wide, implying low efficiency. In this case, the denominator increases, but so does the numerator, and leads us to have the same resolution as before. These are two typical situations that led us to study in more detail the kinetic theory that explains the broadening of chromatographic peaks. Let's see now the kinetic aspects of chromatography. Kinetic theory is a more realistic description of the chromatographic process because unlike the thermodynamic plate theory, which assumes that the equilibration of the solute between the mobile phase and the stationary phase is infinitely fast, kinetics consider the finite rate at which the solute can equilibrate between the two phases. So, the resulting shape of the chromatographic peak will depend on the elution rate. It also depends on the diffusion of the solute along the stationary phase. That assumes the existence of different paths that the molecules can follow when moving in between the stationary phase particles. For example, they twist from one side to the other of the packed particles. A third factor refers to the mass transfer during the multiple equilibria that are established. The three of them are described by the Van Demeter equation, which we are going to study next. The Van Demeter equation relates H in function of the mobile phase speed or flow rate as shown in the blue box formula. Being u the velocity of the mobile phase, A, B, and C are constants for a tandem of stationary phase and mobile phase. They are factors that contribute to the broadening of chromatography peaks by increasing H, which contributes to the loss of efficiency. The figure in the slide shows the typical curve profile for the Van Dimter equation. It's represented H, the theoretical plate height, versus U, the mobile phase flow rate. This equation has three parts. The constant line, which corresponds to the value of A, the green line, the zero asymptote second term, B divided by U, red line, and finally a straight line whose slope is the constant C, blue line. The combination of the three gives the curve represented by the black line. We can see there is a minimum, which is the optimum point since we obtain the minimum theoretical plate height, the optimum efficiency. This occurs for each column according to its characteristics. At mobile phase flow rates lower than the optimum, longitudinal diffusion causes a widening of the band, then an increase in the height of the plate. For higher than the optimum flow rates, the slow solute equilibrium between the phases causes again distension or broadening of the peak. So we are going to analyze separately each equation factor. The first term, A, corresponds to eddy diffusion and considers the different paths by which solute molecules can move through the stationary phase when entrained by the mobile phase. In open tubular capillaries, the A term is 0, since the lack of packing means that no channeling occurs. However, in packed columns, there are multiple distinct pathways, so-called channels, through the column packing, resulting in band expansion, and A is greater than 0. The less the homogeneity of packing material, the higher the broadening due to the formation of these channels, causing diffusion of solutes and consequently peak broadening. Additionally, this effect is proportional to particle size. So, the smaller the particles, the smaller the peak broadens. In the example of the figure, where 3 points for defining a chromatographic peak have been drawn, point 3 represents the mobile phase containing our compound passing freely by the packed material of the stationary phase, and then is coming out faster than the others. Point 2 is the compound in mobile phase passing through small channels formed by the packed particles. This itinerary delays the exit of the compound from the column. Finally, point 1 is traveling through the most irregular particle sizes, which gives a longer path, explaining why this point is exiting in the last position. The term B takes into account the longitudinal diffusion of the analyte through the column as they diffuse from the central zone of the more concentrated band towards more dilute regions. This is happening forward and backward the direction of the mobile phase flow. The higher the mobile phase speed or flow rate, the shorter the residence time of the analyte into the column and the lower the B coefficient. This is why U is inversely proportional to H in the Van Dimter equation. Particle size and column diameter have a direct proportional influence, so the larger the particle size and the larger the column diameter, the higher the B value coefficient. C is the mass transfer resistance, since the solute needs a certain time for equilibrium to be established between mobile phase and stationary phase. Recall that this equilibrium was defined by Kd, the distribution constant. This time is rarely completely reached in chromatographic times, so that molecules are dragged forward before they have fully calibrated with stationary phase. And then molecules at the end of the band are left behind due to the fast movement of the mobile phase. This causes diffusion, leading to peak broadening that is perpendicular to the direction of flow, resulting in a widening of the band. Therefore, the higher the velocity of the mobile phase, the greater the broadening of the peaks due to this phenomenon. Another influencing factor is the pore depth of the particle, since the greater the pore depth, the greater the delay, and then the greater the final peak broadening. Finally, the smaller the particle, the smaller the pore depth, and then the smaller the contribution of C term. These are the three main factors that are directly proportional to the value of C. Notice that the two last diffusion phenomena, B and C, are opposite for the final contribution to H. To summarize thermodynamic and kinetic factors of a chromatographic separation, we can say that the migration of a solute through the column causes a broadening of its band, resulting in two main problems. The first one is qualitative, poor separation of compounds with close retention times. And the second one affects quantification, as wider peaks imply less intense peaks, which usually results in lower detectability, leading in general to poorer sensitivity. Improvement of two peaks separation means improvement of its resolution. It can be achieved by looking at the equation on the slide, which relates resolution to efficiency. We get this equation from the equations of resolution and column efficiency N that are obtained with experimental values. Our aim is to obtain at least resolution values equal or slightly greater than 1.5. Then we must try to increase the factors that are directly proportional to resolution in this equation. These factors are in terms of N, which relates to the efficiency of the column expressed in number of theoretical plates, which is in turn proportional to the length of the column. An increase in column length can improve resolution by increasing N. However, increasing column length also increases the band broadening due to diffusion processes, as we have seen in Van Dimter equation, and the analysis time. Therefore, it's a compromise situation. Other strategies to increase N or decrease H from the Van Dimter equation could be reduce the particle size of the stationary phase, reduce the internal diameter of the column, or optimize the mobile phase flow rate to get a minimum H value. The chromatography separation can also be improved in terms of selectivity, alpha. The second term of the equation represents the separation between two adjacent peaks attending the selectivity. The higher the selectivity, the higher the resolution. This can be achieved by optimizing the mobile phase composition, by reducing the stationary phase layer in liquid chromatography, or by reducing the temperature in gas chromatography. Finally, we can also improve a chromatography separation in terms of retention, K. Increasing the retention of the compounds could improve the resolution. However, there is a practical limit to which it's possible to increase the retention factor, because if retention times get too high, the peaks get too wide. To increase the retention of a compound can be done by lowering the temperature of the mobile phase in gas chromatography, or by changing the composition of the mobile phase in liquid chromatography to increase the affinity of the compounds for the stationary phase. The example on the slide shows the case of the separation of 6 components in the same chromatogram. The first situation, A, the system is defined to obtain good values of K for peaks 1 and 2. However, under these experimental conditions, peaks 5 and 6 are too retained and therefore broad and flat. This may prevent or hinder their quantification. In case B, elution has been accelerated, reducing K value for compounds 5 and 6. However, in these conditions, peaks 1 and 2 are unresolved, as are peaks 3 and 4. The third possibility, C, with the modification of the elution conditions, manages a good resolution of peaks 3, 4, 5, and 6, being not the case of peaks 1 and 2. These three situations are related to the constant mobile phase during the whole chromatogram. In GZ, isothermal conditions. In LC, isocratic conditions. So, to achieve a good separation of the 6 compounds, the mobile phase conditions must be modified during the separation. It's necessary to apply a gradient elution. In the case of gas chromatography, the modification is done by changing the temperature, in other words, to establish a temperature program changing with time. In the case of liquid chromatography, the composition of the mobile phase is modified over time. We're going to see all these situations later on. All the different concepts up to now are more qualitative than quantitative. But one of the main aims of analytical chromatography is to be able not only to identify a compound, but to know the present amount of such compound in a sample. There are several ways to quantify a compound by means of peak height analysis. It's obtained by joining the baselines of each side of the peak and measuring the distance perpendicular to the peak maximum. However, this method is inversely proportional to the peak width, so that in conditions of broadening influenced by column temperature, mobile phase flow rate, sample injection, etc., this measurement may not be very accurate and make significant errors. Peak area analysis is based on the integration measurement of the area contained within the peak. The area is independent of the peak broadening, so it's more convenient to work with this analytical parameter and not the previous one in a general way. The third is the spot area analysis. This is a specific quantification for planar chromatography. It's based on the integration of the whole spot area caused by a compound that has migrated along the layer or coating, similarly as we integrated the peak area in the second quantification mode explained before. There are 3 different possibilities for calibration methods in chromatography. External calibration, where various standards of increasing concentrations of the analyte are measured and linear regression is performed. Then, interpolation of the signal obtained for the analyte contained in the sample is carried out. Here, the biggest error committed may be due to the volume of sample injected, which can cause great irreproducibility, especially in gas chromatography, as we will see in Unit 4. Internal standard calibration, where a fixed concentration of a compound similar to the analyte, called internal standard, is added to all calibration standards, and the ratio of the peak area of the standards versus the ratio of standards concentration are plotted, performing a linear regression as well. The sample is prepared in the same way as the standards and quantified by the peak area analysis. This calibration mode avoids inaccuracies because of the injection volume as well as fluctuations of the equipment measurement, for example. Requirements for a good internal standard are to have similar characteristics to the analyte, to be absent from the sample, and to have different retention time from the analyte. Response factor. In this calibration approach, there is no need to plot a calibration curve. Now, peak areas are corrected according to the detector response by dividing the values measured by the response factor for each analyte and the response of the internal standard. For this method, it's mandatory to precisely know the response factor Fr for each analyte with a specific detector. If the detector changes, Fr may change. This quantification mode is widely employed in gas chromatography.